Hi, I'm Chang. So in this presentation, I'm gonna present to you the final element analysis of OSU formability test. So here's the outline of this presentation. The first part is introduction, second is background, third is modeling techniques following with simulated results. The last, of course, is the summary. So in terms of the introduction, what is final element analysis? Basically, this is a numerical technique for finding approximate solutions, and this is widely used in simulating engineering models. There are basically three types of models we have seen most in the fields of engineering. The first one is classic structure mechanic models. The second one is the fluid dynamic models, and the third one is the thermodynamic models. This method is extremely helpful for professional engineering to modify the engineering models based on the simulated results. So here's the background. The OSU formability testing group is designed to explore the formability of sheet metals under near plane stress conditions. A FEI model is designed based on the operating conditions given by the group. So basically what we do in this project, we just based on the experiment result, we're gonna evaluate the feasibility of FEI models. So in terms of modeling techniques, on your left hand side is the schematic of the experimental setup. On your right hand side is the model, which is created in ANSYS. In this case, symmetry is used in the model, which is modeled from the symmetry line to the right lock bead. So here's the modeling parameters. First is the mesh element. We use 8 node shell elements and mesh them into elements with edge lengths of 0.2 inch. The punch and die are considered as rigid body. Therefore, leave the patch and die unmeshed. For the boundary conditions, we set the displacement in the direction of x and rotation in y direction equals to 0 along the symmetry line of the model. Along the red edge where the sheet metal is attached to the die, we set all degree of freedom equals to 0. In terms of loading condition, I'll ask file for written to simulate the loading. In the first loading step, we set the punch displacement to minus 40 millimeters. For the second load step, we set the punch displacement equals to 0. So we run the FEI models and obtain the displacement, obtain the displaced structure. As you can see from the picture, the maximum displacement is about 1.5 inches. So here's the one missing stress under different loading conditions. From left to right is the first one is the end step results of first loading, and the second is the results at the beginning of the step 2, and the third one, of course, is the results when the punch is detached from the metal. So here are the strain distribution plots of simulated model and experimental testing. As you can see here, they are pretty close, and basically the simulated result capture the general curves of the experimental results. So here's another plot of reaction force versus the punch displacement. In this case, the punch is considered as a rigid block, and the contact conditions is modeled as a point contact. And the contact point could be determined based on the result obtained from the answers. So here's our tabulated simulation results. So finally, the summary. Comparing the results obtained from experimental testing. Actually, the simulation of force and deflection data is pretty good for small deflection. However, at large deformation, simulation on reaction force deviates greatly. However, for the stress and strain values, it holds good approximation in terms of experimental results. So, what factor could cause the deviation? Our first thought is the setup of the material properties, since it is hard to put in material properties very close to real conditions. In real conditions, material deformation really depends on the rate of loading and hardening process during manufacturing. Last but not least, I want to thank you, Professor Dupay. Thank you for your patience. I really learned a lot from this course and really like it. Thank you.